a uniform metal tube of length 5 meters and mass 90 kilograms is suspended horizontally by 2 vertical wires attached at 50 and 150 centimeters. So again, the key thing is to draw a diagram. Again, you just have to be careful with distances. So we've got something that's 5 meters long. We've got so much stuff to label that I think it's probably sensible to not label the 5 meters. We'll label the other parts that we're going to have. So we know its own weight will act from its center. We're going to keep in our head for now that the distance to each end of the pipe is 2.5 meters. We've got 2 supports. One is 50 centimeters from the end. So let's mark that one in now. This is tension, I'm going to call it T1. And this distance, let's use a different color for distance, here should be 2.0 meters. So the total length from W to the end was 2.5, but this distance in here is 50 centimeters. So 2 meters to that support. Then on the other side, the support is 150 centimeters from the end. Or if this distance is 2.5 meters, that makes it 3/5 of the way across, doesn't it, towards the center. So we'll draw it coming from about here, T2, and the distance we can label in. Again, let's use orange, is in here, which now is a distance of 1.0 meters. So we've got 2 unknowns in this particular case. One way to deal with the fact that we've got 2 unknowns is to use some simultaneous equations. One simple simultaneous equation that we could write is that the weight of the ruler, which of course we do know from the 90 kilograms, is equal to T1, T2. The alternative here is to make sure that we pick a point to take the moment where either T1 or T2 provides a moment of 0. So this means there's 2 sensible places around which we can take moments. I'm going to label them A and B. If I choose to take moments around A, then the moment of the force T1 around A is equal to 0. So if I go from A, I've got this force acting. I know this force has a size which is equal to 90 times the gravitational field strength, so 90 times 9.81. So we've got, taking moments around A clockwise, a force of 90 times g at a distance of 2, plus the anti-clockwise moment, which is T2 times 1, and this should be equal to 0. This being times 1, of course, makes life simple, because we can just say then that T2 must have a magnitude equal to this. So that's 90 times 9.81 times 2, which gives us a value of 1,765.8. When we're writing this down, we should write it, so we're slightly ambiguous on significant figures, aren't we here? Let's go with 2, so 1,800 newtons. This is wrong. This is not at a distance of 1 from A, is it? This is at a distance of 3 from A. Let's try that again. 3.0. This looks better. So now we can say T2 is equal to 180 times G, 9.81. That's just combining the 2 and the 90 to get 180, divided by 3.0. This looks more hopeful. So I'll divide my previous answer by 3, which gives me a value of 590 newtons. So 589 if you're writing it to 3 significant figures, but 590 newtons if you're writing it to 2. Then to find the size of T1, we could do vertical forces on the bar. They should add up to 0 because it's an equilibrium, or we could take moments around B. I'm going to do the latter because that's the main idea we're practicing at the moment, but obviously either works. So let's be more careful this time. From B, the clockwise moment is provided by T1, which is at a distance of 3 meters. The anti-clockwise moment is provided by W, that's 90 times the gravitational field strength, at a distance of 1 meter from the pivot. So those have to equal to 0. If we compare it to what we had last time, the only difference, of course, is this factor in here. So we could immediately perhaps say from this that T1 must have half the size that the previous one did. So if we work it out, let's work it out properly. So it's going to be 90 times 9.81 divided by 3.0. So that gives a value of 294. So we're going to write it as 290 newtons to 2 significant figures, or 294 to 3 significant figures is okay. So yeah, we can't quite just half our result here, can we, because of the rounding that was involved along the way.